IIR filter design. So digital and analog filters both take out unwanted noise or signal components, but filters work differently in analog and digital domain. Analog filters removes the signal above a certain frequency are called low pass filter because they are not low frequency signals because they let low frequency signals pass through a filter while blocking everything above the cutoff frequency. An analog filter removes all the signals below a certain frequency is high pass filter because it passes everything higher than the cutoff frequency. Analog filter is typically used in electronics and is considered as a basic building block of signal processing. These among the filters are used to separate audio signals before applying to a loudspeaker, to separate and to combine several telephone conversations onto a single channel can be done using analog filter. To select a particular radio station from the radio receiver by rejecting all other channels can be done using analog filter. Analog filters are the circuits made up of analog components such as resistor, capacitor, inductor, and op-amp. Digital filters are often embedded in a chip that operate on digital signals such as MCU, SoC, processor. Analog filters are analog filters are fairly simple but increase in complexity. Digital filters can be more precise in filtering, but the signal must be digital. Placing a digital filter in analog signal chain would require the analog signal to be converted to digital signal before the digital filtering could be applied, and with any conversation there are trade-off in a signal integrity. The digital filters work by oversampling and averaging and are programmable, but it is wise to apply an analog filter prior to the signal conversion and in but it is wise to apply analog filter prior to the signal conversion so that all unwanted frequencies above or below when the desired signal is reasonably expected to operate are removed. First, the conversion process and choosing an analog to digital signal converter is in itself a careful process that involves choosing a sampling rate that will avoid aliasing during the conversation. Therefore, choosing an ADC in itself a task that requires careful attention. Next is IR filter design by approximation of derivatives. So IIR filter design by approximation of derivative. Analog filters having a rational transfer function just can be described by the linear constant coefficient differential equation. One of the simplest method for converting an analog filter into a digital filter is to appropriate the differential equation by an equivalent difference equation. This approach is often used to solve a linear constant coefficient differential equation numerically on a digital equations. For the derivative dy of t by dt at time t equal to nt, we substitute the backward difference equation. So equation will be like this, where t represents the sampling interval y of n equal to y of n of t. The analog differentiator with output dy of t by dt has the same function hs equal to s, while the yn of minus 1 by t has been transfer function h of s is equal to 1 by t, that is Z transform, inverse Z transform. Consequently, the frequency domain equivalent to s is equal to 1 minus z raised to minus 1 by t. The second derivative is replaced by the second difference equation. In the boundary, in the force frequency domain, equation 3 . So it is easy to generalize the equation that s of k, s raised to k is equal to 1 minus 1 by z by t raised to k. As w varies from minus infinity to infinity, the corresponding locus of the point in z plane is a circle of radius 1 by 2 and with center z is equal to 1 by 2 as shown in . So converting the simplest method to convert an analog filter to a digital filter. So IR filter designed by the approximation derivative. The simplest method to convert an analog filter to a digital filter is to convert differential equation into equivalent difference equation. So this is the equation. The next is for the analog derivative. The system function is given by hs is equal to s, and the digital system function is this. So the second derivative is replaced by the second difference, that is d2 of y of t. And this one is the equation, and in frequency domain it is equivalent to this. The next is system function for IR filter obtained as a result of approximation of the derivative is hz is equal to h of s. Let us investigate the implication of the mapping from s plane to the z plane. So z is equal to 1 by 1 minus st. Then the j omega axis is mapped into this equation. The y-axis in the s-plane is mapped into a circle of radius and with center z is equal to 5. So any point in the left hand plane will be mapped to a points inside that circle. So the resultant filter is stable. The possible location of the poles of the digital filter are confined to a small frequencies. As a consequence, the mapping is restricted to low pass filter and band pass filter with relatively small resonant frequencies. It is not possible to transform a high pass analog filter into a corresponding high pass digital filter. So, in attempt to overcome these limitations, more complex substitutions for the derivatives have been proposed. The resulting mapping between the S-plane and the Z-plane is given by this equation. When Z is equal to e raised to j omega, and equation for S is given by, which is a pure imaginary equation, and which means by carefully selecting values of a k of S. A j-omist axis can be transformed into unity circle, and it can be done by using optimization. So this is one of the example for conversion of analog bandpass filter with system function given by this equation. So we convert it into a digital IR filter by substituting the derivative method, and we will solve it, and t should be less than or equal to 0.1 for poles near the unity circle. This one is the second example. So next is IIR filter by impulse invariance method. In this design method, we want the digital filter impulse response to look similar to that of frequency selective analog filter. Hence we sample h of t at some sampling interval t to obtain h of n. So first is mapping a continuous time impulse response to discrete time, and second one is mapping a continuous time frequency response to a discrete time. Mapping a continuous time impulse response to discrete time, and mapping continuous time frequency response to a discrete time. So the analog and digital frequencies are replaced by omega is equal to mt or e to j omega. If the continuous time filter is band limited, then equation will be like this. So the impulse invariance method of IIR filter design is based upon the notion that we can design a discrete filter whose time domain impulse response is sampled version of impulse response of a continuous analog filter. If that analog filter has some desired frequency response, then our IR filter will yield a discrete approximation of that desired response. So this diagram shows that two filters, analog filter and IR digital filter. Input and output of analog filter is analog, but in digital it is not. But in output or input of IR digital filter is not digital, it is impulse response output. Next is bilinear transformation method. The method of filter designed by impulse invariance suffer from aliasing. Hence, to overcome this drawback, bilinear transformation method is designed. In analog domain, frequency axis is an infinitely long straight line, while sample data z plane, it is unit circle radius. The bilinear transformation is the method of squashing the infinite straight analog frequency axis so that it becomes a finite. There are some important features of bilinear transform method. That is, the first one is bilinear transformation method is a mapping from analog S plane to digital Z plane. This conversion maps analog pole to a digital pole and analog zeros to digital zeros. Thus, all the poles and zeros are mapped. This transformation is basically based on numerical integration technique. used to simulate an integer of analog filter. This is one of the correspondence between continuous time and discrete time frequency points. Entire range in ohm is mapped only once into the range minus pi to plus pi. Frequency relationship is non-linear. Frequency wrapping or frequency compression is due to non-linearity. Frequency wrapping means amplitude response of digital filter is expanded at the lower frequencies and compressed at the higher frequencies in comparison of the analog filter. But the main disadvantage of frequency wrapping is that it does not change the shape of the desired filter frequency response. In particular, it changes the shape of the transition band. Next is the difference between impulse variance versus bilinear transformation. So the first difference is in impulse variance. In this method, IR filters are designed having a unit sample response, that is sampled version of the impulse response of analog filter. In bilinear, this method of IR filter design is based on the trapezoidal formula for numerical integration. In impulse invariance, small value of t is selected to minimize the effect of aliasing. In bilinear, this transformation is conformal mapping that transforms G omega axis into the unit circle in the Z plane only once, thus avoiding aliasing of frequency components. Impulse invariants are generally used for the low frequency like the design of IR, LPF and limited class of bandpass filter. While bilinear, these are used for designing low pass filter, high pass filter and almost all types of bandpass and band stop. In impulse invariance, frequency relationship is linear, and in bilinear, frequency relationship is non-linear. In impulse invariance, all poles are mapped from the S plane to the Z plane by the relationship Z raised to k equal to e raised to pkt. But the zeros in two domain does not satisfy the same relationship. While in bilinear transformation, all poles and zeros are mapped. Thank you.